Why is nested interrupt handling so complex in microcontrollers? Imagine you're trying to juggle multiple balls at once. Each ball represents an event needing attention from your microcontroller. Now, picture some balls being more urgent than others. Handling this efficiently is what makes nested interrupt handling so tricky. When a microcontroller is running a task and another event suddenly becomes more important, it needs to pause, save its current work, and switch to the new task. But if another even higher priority event comes in while it's handling the second, the process gets even more complicated. This is the essence of nested interrupt handling. In simple terms, an interrupt temporarily stops your main program to deal with an event like a button press or sensor signal. When nested interrupts are enabled, the microcontroller can interrupt an ongoing interrupt service routine with a higher priority event. To do this, it must save everything about the current task, like register values, the program counter, and status flags. This saved information is stored on the stack, which is a special part of memory. Once the higher priority task is finished, the microcontroller must restore everything exactly as it was before. This process needs to be precise to avoid losing data or causing errors. One big reason nested interrupt handling is complex is because of context management. Each interrupt needs its own set of saved data, and stacking multiple contexts can quickly fill up the stack memory. If the stack overflows, the system can crash or behave unpredictably. Managing priorities is another challenge. The microcontroller must decide which interrupt to handle first, based on priority levels. This requires hardware support like priority registers or interrupt controllers that can dynamically assign and preempt tasks. Without this, the system might get stuck or miss critical events. Race conditions also come into play. When multiple interrupts access shared resources like variables or hardware, conflicts can happen. If not protected properly, data can become corrupted. Engineers often use techniques like disabling certain interrupts temporarily or using atomic operations to prevent this. Timing is another concern. Handling nested interrupts can increase latency, meaning some lower priority tasks might get delayed. This can be problematic in real-time systems where timing is critical. Stack usage is a big factor. Each nested interrupt pushes more data onto the stack. If nesting goes too deep, it can exhaust the available memory, leading to crashes. The return mechanism is also more complex. The microcontroller must keep track of where to return after each nested interrupt, especially when switching between different modes of operation. Advanced microcontrollers like those based on Mcortex and processors have hardware features to help with nested interrupts. They include nested vector interrupt controllers that manage priorities and reduce overhead through techniques like tail chaining. But even with these tools, designing efficient interrupt routines is essential. Keep ISRs short, avoid heavy processing, and use priority management wisely. In real-world embedded systems, nested interrupts are vital for handling multiple asynchronous events such as sensor readings, communication signals, or control commands. But they requiring careful planning, testing, and validation to ensure the system remains stable and responsive under all conditions. So, the complexity of nested interrupt handling comes from the need to balance responsiveness, data integrity, and system stability, all while managing multiple layers of events happening at once.